I'm Jack Burke, editor of Diesel and Gas Turbine Worldwide magazine. And thank you once again for joining us for this seminar or webinar on hydrogen realities, sponsored by Burkhardt Compression. I think this is going to be a very interesting discussion. We have three experts in the field who are going to come at the issue from different perspectives and give us insights into the industry and what they're seeing both in research and in applications. So without further ado, I'd like to introduce our first speaker. Before I begin, I should say, you'll see a box on the screen where you can ask questions of our speakers. Once each speaker finishes, I will answer or ask some of the questions to that speaker, and then we'll go on to the next speaker. If we have time at the end, we'll follow up with some more questions. All right. Well, first off, I want to make sure I get everything correct. Dr. Jacqueline O'Connor was director of Penn State Center for Gas Turbine Research, Education, and Outreach, one of the only places in the world with research addressing every single part of the gas turbine, as well as the systems they integrate with. Hello, Dr. O'Connor. Thank you for joining us, and I appreciate it very much.
Thanks, Jack. I'm going to quick share my screen here and go to my slides. Thank you, everybody, for attending. It's really exciting to be invited to speak on this extremely interesting topic of hydrogen realities. Since I'm the first speaker, as well as sort of the one of the professors of the group, I thought I'd kick us off today by just baselining and providing some foundations about hydrogen and some of the challenges and opportunities for integration into the energy space, so that we can go to Dr. Goldmere and Dr. Hoff and look at some of the more applied issues. Before I go on, I just want to introduce myself and my group a little bit. Like Jack said, I'm the director of the Center for Gas Turbine Research, Education, and Outreach. We do research and development in a number of different areas, as you can see on the screen. But since we are a university group, our main focus is educating the future gas turbine workforce with a particular focus on the graduate level. We do outreach as well, which is why I'm here today. So if you have more questions or want to get in touch with us, please check us out as our website, which is down at the bottom. All right, so I'm going to talk about three things today. First, just a quick introduction to hydrogen. I'll give a bit of a shout out to a podcast that I did with Dr. Goldmere a few months ago, the GE Cutting Carbon podcast. And on my episode, we were talking about hydrogen and gas turbines, and I referred to hydrogen as a sneaky little molecule. And I think that's a good way to think about it, because and there's sort of a lot that has a lot of different connotations, which we'll talk about. I'll talk about some hydrogen combustion basics. My background is in combustion. And that will set up some of our discussion for challenges and opportunities and some more of the applications that Dr. Goldmere and Dr. Hoff will talk about. So let's talk about this sneaky little molecule. So hydrogen is the lightest element on Earth, but it packs a real punch as a fuel. So, periodic table, hydrogen's all the way up on the top left. In its natural state, it lives as two hydrogen atoms stuck together. There's some basic physical properties on the left, a couple that I want to point to. One is this boiling and melting points. This goes to some of the storage issues that folks have raised about hydrogen. You have to cryogenically freeze it in order to get it into a liquid storage state. The other thing that we'll come back to in a bit is this issue of diffusivity. This is hydrogen, because it's so small, it only has a molecular weight of 2 grams per mole. It can fit into a lot of different places, which means that handling things like seals and valves that maybe were designed for higher hydrocarbons, things like natural gas, are not necessarily compatible with hydrogen. So there are also a bunch of combustion issues that arise because of this diffusivity, which we'll talk about in a second. But as a fuel, it has one great advantage, which is its mass-specific energy density, which is humongous. I'll show this in a comparison chart in the next slide. Sort of doesn't really match up on the volume-specific density, but then something where I think there are both challenges as well as opportunities is the flammability limits. Hydrogen is extremely reactive, which means that even small amounts, 4% in air, all the way up to 74 or 75% in air at standard temperature and pressure, you can get it to burn. This is a little bit scary from a safety standpoint, but also opens a lot of opportunities in the combustion space. Most hydrocarbons, except for something like acetylene, has a much lower flammability range, and so it's actually a great fuel to burn. The other thing, which I'm sure will come up in our discussions, is when you burn it, you're not producing any CO2. So I thought, based on the technologies that we're going to talk about today, it would be good to do just a quick comparison compared to other fuels. I have hydrogen as compared to methane, which is mostly what natural gas is comprised of, particularly here in central Pennsylvania, sitting on top of the Marcellus. And then diesel and gasoline for transportation and some power generation applications. So we already talked about its power density and the mighty little molecule. But some of these numbers on the bottom, mass diffusivity, something called adiabatic flame temperature, and then flame speed, are all really critical for how hydrogen burns inside of combustion technologies. You can see, as compared to methane, again, the major constituent of natural gas, these numbers are quite different. Mass diffusivity almost 4 times that of methane, a 300 degrees Celsius difference in adiabatic flame temperature, and then almost an order of magnitude difference in flame speed. As compared to diesel and gasoline, it doesn't really make sense to talk about mass diffusivity there, since these are liquid fuels. Burns a little bit hotter than these heavier hydrocarbons, and again has a much higher flame speed. And so what I want to talk about for the rest of my time here is what implications these really different physical properties have for combustion properties, and how hydrogen is going to work as a fuel in these engines. So let's start with adiabatic flame temperature. So the adiabatic flame temperature, it's a sort of a concept that tells you what the maximum possible temperature of a reaction is. So combustion reactions are exothermic. That means if you add fuel and air, you end up with products and heat. More realistically, what we're saying is that because it's exothermic, the products are at a higher temperature than the reactants. And that highest possible temperature you can reach, if you don't have any heat loss or incomplete combustion, those sorts of things, is this adiabatic flame temperature. And so, like I showed, for, let's say, land power based gas turbines, which is where a lot of my particular research is in, the adiabatic flame temperature is about 300 degrees Celsius higher than that of methane or natural gas. And there are some challenges and opportunities that come with that. I teach introductory thermodynamics here at Penn State, and so the opportunity really comes from that. If we think back to our basic cycle analysis, this is our nice Brayton cycle here. If we can really push up this highest temperature, we can push up the efficiency and hence the power extraction from a cycle. So this is our Carnot efficiency down here. And so if we can get the combustor to run hotter, which you could with a hydrogen fuel, then you can run your system more efficiently. The problem is, and my many colleagues at Penn State who work in turbine aerothermal remind me of this on a regular basis, is that the combustor is not operating all by itself. There's hardware downstream. The hardware downstream is also spinning, which means that there are not just thermal, but also mechanical loads on these parts. These are relatively old charts because it's difficult to find new charts about exotic high temperature nickel alloys. But what you can see is that this is 100-hour rupture stress per density of different high temperature alloys as a function of operating temperature. And this chart only goes up to 1300 Celsius, which doesn't even get close to those temperatures that we're looking at for even natural gas fuel, never mind hydrogen. And so there are a lot of challenges associated with the durability and just basic operation of the hot section of the engine because of the high temperatures. So from a thermodynamicist standpoint, excellent. From a heat transfer standpoint, quite a challenge. The other piece of this is flame stabilization, and this is getting much more into my own research. The flame speed, which I mentioned, hydrogen has almost an order of magnitude higher flame speed than that of natural gas fuels, as well as diesel and gasoline. The flame speed is the speed at which flames propagate normal to themselves. So I always show this when I teach Intro to Combustion. if you had a tube with fuel and air flowing through it and you wanted the flame to be stationary in that tube, you'd want the velocity coming into the flame to be equal to the flame speed. That matches what's called the kinematic condition. And so this SL naught, we call this the unstretched laminar flame speed. But this is, you can actually derive this quantity just from the chemical and physical properties of a gas mixture. So you know, things like diffusivity and heat of combustion and density make up this flame speed. What I'm showing here are some flame speeds at standard temperature and pressure of a bunch of, interesting fuels. This is from a classic combustion textbook by Glassenhader and Glumac. On the x-axis is equivalence ratio, which is a normalized fuel-air ratio, where 1 here is a stoichiometric mixture. And there are two things that I want you to notice about this graph. The first is that the y-axis has units of centimeters per second, which is not a lot. These flames don't move fast. And then the second thing is I want, you can see the little break in the graph here. I want you to notice how much faster, for a huge range of equivalence ratios, hydrogen flame speeds are than pretty much every other fuel, particularly natural gas, which again, when you're talking about a bunch of land-based applications, this would be what you'd be replacing. So there are some real challenges associated with, from a combustion standpoint, replacing hydrogen or replacing hydrocarbon fuels with hydrogen. I tried to be an optimist and think about opportunities associated with this, but I honestly couldn't come up with any. I just came up with challenges. So this is a plot actually I took from my PhD thesis. It was a good blast from the past, but it shows the basic flow field of what a gas turbine combustor injector would look like. So you have a swirling flow field, it creates a lot of recirculation, a lot of shear. These are the fluid mechanic mechanisms that we use to hold a flame in place. But at each location along this flame, this kinematic condition is being met. And obviously, because you're at higher temperatures and pressures, your flame speeds are higher, but still that gulf between natural gas and hydrogen is still there. The bottom shows some recent results from my lab. If you look at the left hand of these images, these are chemiluminescence images from flames of natural gas and hydrogen, where we went from 10% hydrogen to 20% hydrogen. And what you can see is that the main bulk of the flame here moved closer to the injector because the flame speed went up. And this is not a whole lot of hydrogen. We could run this rig up to about 40% hydrogen before it got a little scary and we were afraid that the flame was going to flash back into the hardware. So even small changes in hydrogen can have dramatic effects in flame holding, which has other effects in terms of your durability and your operability of your engine. So this is my last slide. I just wanted to bring up that last point. This is a bit of a shameless plug for the work that we do in my lab. All of these really fundamental properties of hydrogens, things like its diffusivity, its flame speed, its adiabatic flame temperature, have large-scale systematic implications in complex technologies like gas turbines and diesel engines. So this was work where we changed the amount of hydrogen in natural gas going from less to more. And you can see this is the combustor pressure oscillation, goes from okay to quite loud. We did a lot of flame imaging to explain why this was. This is the paper that just recently came out on this, but it all goes back to those really fundamental quantities. And this is quite a complex system level issue. So with that, I'll conclude. I just want to say I work with a really great group of both colleagues and students at Penn State. All the work we've done in hydrogen has been funded by the US Department of Energy, so many thanks to them. Yeah, I'd be very happy to take any questions.
All right, thank you, Dr. O'Connor. I appreciate that. That was very interesting. Well, we've gotten several questions about whether the slides will be available. Is that something that you could share?
Yeah, this is all publicly available.
Okay. I also had a question. With higher temperatures, I assume there are problems with NOx formation when nitrogen is present. In a gas turbine fueled by hydrogen, would you normally be using ambient air as your oxygen source?
Yes, so that's one thing that I didn't mention, but I'm really glad somebody brought that up. Absolutely. you have this trade-off in most combustion technologies that you know, as you raise your temperature, you're increasing your NOx emissions. As you start to lower the temperature, there are other things like unburned hydrocarbons and CO that can become an issue. And so usually you're playing this trade-off between the two. So yes, not only do you have durability issues, but you also have emissions issues as a result of the higher adiabatic flame temperatures.
Okay, let me see. What mixture ratio H2 high hydrogen stay or would be ideal for typical power generation applications? Is that something you can say at this point?
I will also defer to my other two panelists to get their perspective, but I think the answer is no. And it's because there's no one perfect one. If there was, then I don't think we'd be having a panel on this right now. Right? There are so many trade-offs that you're working with, right? You're working with durability, you're working with emissions, you're working with all these operability issues, that it's also quite dependent on the design of the technology itself. And so, no, I don't think there's any one global optimal. And you know, again, just because everything is so hardware and system and operating condition dependent.
Okay, thank you, Dr. O'Connor. All right, I think that was very interesting. A good start to the conversation, getting into the basics, fundamental research going on. Right now, I'd like to introduce, well, for hydrogen to play a major role in decarbonization, solving challenges around its transportation, storage, and distribution will be key. All those steps involve compression. Which brings us to Dr. Klaus Hoff, our next speaker. He's Managing Director of Compressor Solutions at Nguyen and Esser Group. Hello, Dr. Hoff. Thank you for joining us.
I unmute first, then I share my screen.
There you go.
And then I hope you can see my presentation. Can you see that?
Yes, I can.
Yeah, fine, excellent. Yeah, okay, my presentation will be about the appropriate compression principle for hydrogen, of course. We as a manufacturer of reciprocating compressors are very interested in that, since we think this future demand of hydrogen will help us to keep in the business. And I will explain with my presentation why I'm convinced that this will happen. Yeah, the first of my presentation will be, I will give you an overview of the compression principle we have, which are available. And afterwards, I will show you some physical basics and the advantages and disadvantages, especially for the centrifugal and the reciprocating compressors. All the others, in my opinion, will not take a role in this hydrogen. Only these two compressors will be part of this. Then I will talk about the efficiency and flexibility advantages of reciprocating compressors compared to the centrifugal compressors, and in the end I will summarize it. So, overview of compression principles. I've shown, here are some pictures. We have two basic principles. The first one, and this is a very common one, is the fluid dynamic principle, which is widely used for many gases. And here we can distinguish between axial compressors, centrifugal compressors, and these centrifugal compressors are subdivided in single shaft compressors, as you can see here, or even integrally geared ones. I took the pictures from Siemens because I worked for Siemens 20 years ago. So originally my expertise is a turbo compressor expertise, and then I changed over to the reciprocating compressor business. But I know I was exactly in this barrel type compressors. I was in the development department to that time. On the other side, we have the positive displacement principle. One of the major principles is the reciprocating compressor. And here we can distinguish between piston compressors, as shown here in this picture, and so-called diaphragm compressors. Most of them will never heard about diaphragm compressors. This is a special kind of a piston compressor where the piston does not directly compresses the gas. In between, we have oil or liquid, and the liquid is pushing the diaphragm, and the diaphragm is pushing the gas. But it is, in principle, all the other points and aspects, it's a reciprocating compressor. And then, of course, we have the wide field of rotary piston compressors. And here I just named the sliding vane compressor, for example. And the most important one is, of course, the screw compressor, as seen here in the picture. Important for the people who think about selecting a compressor, of course, is which pressure and which flow can I achieve with which compressor. First, I would like to say, especially for this hydrogen energy change, most likely it is not allowed to have oil in the gas. And this question must be answered first, of course. By principle, the turbo compressor will never add oil to the compression. So the gas is oil-free. By screw compressors, it can or cannot be. So there are oil-flooded compressors available and non-lubricated. So if the demand is non-lubricated, it is feasible. And then the same is true for reciprocating compressors. Reciprocating compressors can be used as lubricated compressors. Then they run very long without any maintenance interval, or you have the non-loop system, then the intervals between the maintenance are shorter. And here this map gives an overview of the different principles in terms of maximum possible discharge pressure and the flow. And the first group, of course, I started with the positive displacement compressors, so reciprocating compressors. And what you can immediately see is when you have an application where you need a very high discharge pressure, then you have no other chance than to use a reciprocating compressor. In this field, especially, we have the so-called hydraulically driven piston compressors, or more used the diaphragm compressors. The diaphragm compressors can easily reach 2,000 or 3,000 bar as discharge pressure, and we can go at least up to a standard cubic meter flow per hour of 1,000 in this range. So, of course, lower flows but higher pressures. This is a typical situation. When you would like to go up with the pressure, then you are typically limited with the flow. The reciprocating compressor, the classical reciprocating compressor, can also reach very high pressures. So there's a special reciprocating compressor out, which is called hyper. This is a compressor for a special application. And with this compressor, you can reach 2,000, 2,500 bar discharge pressure. The classical reciprocating compressor are good for 700, 800 bar, but they can really go also up to high flows. Typically, this is not known. For the big reciprocating compressors, we can also achieve flows in the range of 100,000 standard cubic meter per hour or even more. The other group is the rotary positive displacement compressors. They are good for lower flows. The screw compressors are typically used up to 40 bar. So if you have an application where the pressure is not high, then a screw compressor, of course, is a good choice, especially for air. In the application, the screw compressors, at least when we're in a range of 10 to 20 bar, they dominate this application. And then we come to the last big group. These are the turbo compressor group. And here it's clear we come to the really high flow demand. So an axial turbo compressor can reach very high flows with good outer dimensions. So by the high speed of these type of compressors, we can reach very high flows with acceptable outer dimensions. This graph is general valid, but it would not be acceptable for hydrogen. So for gases with a higher molecular weight, it is valid, but when you come to hydrogen, you have to see it a little bit different. Yeah, what are the advantages, disadvantages, and that is, I bring some slides to that, the physical basics for the centrifugal and the reciprocating compressors. Yeah, the advantages of positive displacement compressors. We can reach a very high pressure ratio per stage, very high. So from diaphragm compressors, you can reach even 7 or 8 as a pressure ratio in one stage. When you are looking for minor flows with an excellent efficiency, then the positive displacement compressor is a good choice. And when you are looking for perfect metering of the flow, then also it's a good choice. And the next 3 points are only valid for reciprocating compressors. You have the possibility of a perfect adjustment to varying suction and discharge pressure without any additional measures and without loss of efficiency, just by the fact that we use self-actuating valves. So the compressor adjusts its behavior just to the suction and discharge pressure. And typically you have almost no loss of efficiency. And of course, there's another important point. We have perfect options to control the flow without loss of efficiency. So if you have an application where you need to control the flow and would not lose efficiency, then the reciprocating compressor should be the first choice. And that is especially true for hydrogen, because hydrogen is a very, very light gas and has the tendency to leak everywhere through. It is for a reciprocating compressor, it's almost without any leakage. Of course, the turbo compressor principle has a lot of advantages. So it's clear most of the compression principles which we see out in the field are done with the turbo compressor. So the turbo compressor is really dominating the compression principle. That must be stated for good reasons. The turbo compressor has very small dimensions compared to the flow. We can reach really huge flows with reasonable compressor dimensions. So just by the fact that the speed is so high, we can reach high flows. The flow itself is continuous. So we have no pulsation with low tendency of pipe vibration. This is an important point. People who are running compressors like the turbo compressors just for this behavior, because they never see vibration issues. That is a difference to the reciprocating compressor. By the discontinuous flow of the reciprocating compressors, pulsation must be handled, and vibration is something you must take care of. Then, of course, there's no inertial load. So you don't need big foundations, and you have no tendency of compressor and foundation vibration. And that is also a plus for this. It's a very reliable machine with lowest maintenance effort. So typically in a refinery, a turbo compressor runs for 5 years without any interruption, 365 days, 24 hours. And after 5 hours, they have the maintenance interval. Now, some formulas, not too much, but I just would like to share you why is it difficult to compress hydrogen with a turbo compressor. In principle, you need three equations. The first one is the conservation of momentum, the so-called Euler Equation. And here I just give a relationship. So the specific power, this is a power divided by the mass flow, is proportional to the impeller circumferential speed. So the higher the speed, the more power. Then we need a relationship between the pressure differential of a stage and density and a specific power. So this is a combination of the first and second fundamental law of thermodynamics. So the pressure differential is proportional to the density and the specific power, and that means it is proportional to the molecular weight of the gas and the specific power. And then we have another restriction we have to look for. These are the stresses in the impeller itself. So it's clear high circumferential speeds will create stresses in the impeller. And then, of course, we have an upper limit there. And there we have to be careful. And here the relation is the stress are proportional again to the square of the circumferential speed. So there are two relations. Either the one or the other is a limit. So the first one is the pressure differential is proportional to the molecular weight and the speed of sound, speed of the impeller. Here, this equation is the limiting equation when the speed of sound of the gas is low, because then typically we have to be with the tip speed below the speed of sound. Otherwise, you have transonic flow at the impeller, and then at least loss of efficiency. So you have to be careful. So the tip speed of the impeller is the design is typically below the speed of sound. Or if the speed of sound is very high, and this is true for hydrogen, then the stresses in the impeller are the limiting factors. So both have to be taken into account. And now I give just with this equation, you can create a relation between a pressure ratio of a given impeller, for example, designed for air, and you can just say with this impeller what is feasible, what pressure ratio is possible for hydrogen for a hydrogen application. And that is a very simple equation. So you just have to use the ratio of the molecular weight of hydrogen to air, and then calculate it with this equation. And then you get the pressure ratio of the same impeller just used for a hydrogen application. And here, just to give you a number, a typical tip speed of an impeller for an air compressor would be 280 meters per second. The molecular weight of air is 28, and for hydrogen 2, for air, it is easily possible to create with one impeller a pressure ratio of 1.4, and applied that for hydrogen, just applying this equation, we only have a pressure ratio of 1.03, almost nothing. So when you try to compress hydrogen with this impeller, you need a lot of impellers to create a pressure ratio. For this example, you would need 12 hydrogen compressor stages instead of one air compressor stage to create the same pressure ratio of 1.4. In reality, of course, this is not the limit for hydrogen compressor. In reality, due to the high speed of sound, a higher pressure raise is possible, since the speed of sound does not represent a technical limit because it's far above. It's above 1,000 meters per second. So now we have to look what is the limiting stress in the impeller. And from what I get from my former colleagues from Siemens, at the moment, at least, industry standard is 380 meters per second as the upper limit of the tip speed. And when you apply that, then you can create a pressure ratio of 1.08. Of course, it's better than that, but it's of course far away from 1.4. So even for that case, taking into account that you can increase the speed, you would need 5 hydrogen compressor stages instead of 1 air compressor stage to create the same pressure ratio. And for a typical pressure ratio of 3, for example, in an application of a pipeline compressor or even a gas storage compressor, you typically need such a pressure ratio of 3. Then you would need 14 hydrogen compressor stages to get this pressure ratio. So a lot of impellers. And then there's another disadvantage compared to a recip. I can't share you the details here, it's too short time, but you can roughly say you need 50 to 70% more power with a centrifugal compressor compared to a recip to create the same pressure ratio. And when you see that in the end, in the hydrogen transition, we will need a lot of power for doing the compression, then this is a lot. Let's come to the performance maps. Here on the left, you see the performance map of a reciprocating compressor, and on the right, you see it for a centrifugal or turbo compressor. These lines are lines of constant speed. Here in this map, that are these lines. And what you can immediately see is a pressure ratio. Each and every pressure ratio can principally reach with one and the same speed. So there is no physical limit for the pressure ratio. There is a physical limit, honestly, but no real physical limit. So you can reach every pressure ratio. You have to look at the temperature, discharge temperature, of course, and you have to look to the load capability of your frame, because high pressures will definitely create high loads and the frame does not be overloaded. But there is no thermodynamical limit. This is different to the turbo compressor. So here in this performance map, you see the lines of constant speed. It's clear when you try to, or if you need high pressure, then at least the first thing is you have to increase the speed. With lower speeds, there is only a small pressure ratio possible. When you need more, then the speed must go up, that's for sure. And that is very important, there is a limit for turbo compressors, a so-called surge line. So beyond this surge line, you can't run the compressor because there are backflow conditions and these conditions will destroy the impeller blades. So you must remain in this area. This is not true for the reciprocating compressors. There are other restrictions, mainly the load restriction, but they have no real thermodynamic restriction. Some words to the dimension. I think this is very easy, of course. It is not the complete story, but just to get an idea. The fundamental relation to understand the compressor size is the volume of a turbo compressor related to the volume of the piston, just the volume of I need at suction side of the gas is proportional to the ratio of the piston speed to the turbo compressor speed. And then some rough numbers. So speed of recip is in the range of max 1000 RPM. It is already upper end. So the typical big reciprocating compressor has lower speeds, but this is, let's say, even for bigger compressors is the upper speed limit. And for turbo compressor, we are easily in the range of 15,000 RPM. So from that, the dimension of a turbo stage is 1/15 of a reciprocating stage. And that is the main reason why the turbo compressor is typically preferred, because you get a very small compressor for the same kind of compression task. But we learned for hydrogen, we need a lot of impellers. 14 stages are needed instead of one reciprocating stage for a compressor ratio of 3. That means dimension of this compressor is in the range 14, because 14 impellers divided by the ratio here 15 of a recip. So the overall dimensions of a centrifugal compressor for hydrogen are, they may, in the end, they will be smaller, but they are on the same level. Okay, then I come closer to the reciprocating compressor and will share you with some slides the efficiency and the flexibility advantage of a reciprocating compressor. Here with this picture, I would like to explain. It is easy, it's very easy to understand how a reciprocating compressor works. So we have a frame with a crankshaft, connecting rod, crosshead, piston rod, and here the compression takes place. So we have a cylinder with a piston moving back and forth, and here by these crosshead compressors, we have in one cylinder 2 compression rooms. So here on the crank end side and here on the head end side, and the cycle is pretty easy, and is explained here with a so-called PV chart. So here's pressure against let's say volume, and I start here in the bottom dead center. So here the piston is at the bottom end. We look at the head end compression chamber. The suction valve closes because the piston is compressing gas, and then the self-actuating valve will close. The compression starts, and when the discharge pressure here in red is reached, then automatically the discharge pressure opens and the compressed gas is discharged to the discharge side. At the top depth center, the piston is going back and the discharge valve closes, and we have the so-called back expansion. This is the main influence on the so-called volumetric efficiency. And the reason for that is, even when the piston is at top depth center, we have a so-called clearance volume. So there's a small amount of volume remaining in the compression chamber, and this volume needs to be back expanded down to the suction pressure. And therefore, here at this position, the suction valve opens, and now fresh gas is sucked in, and the cycle begins again. So this is a so-called volumetric efficiency. The maximum possible flow would be this length, and the real flow is from here to here. So the ratio of this length to that length would be the volumetric efficiency. And the design task, of course, is to create the smallest clearance volume as possible, because you improve the volumetric efficiency then. Now, what are the main applications? So we do this business for a very long time, and as long as gas is compressed, you need a compressor, that's clear. And as long as hydrogen is compressed, you need reciprocating compressor. So the main applications where we deliver the compressors are refinery, especially refinery, but also petrochemical and chemical industry. We have experience up to 700 bar. And this statement is a clear statement. Wherever hydrogen is compressed, it is usually a reciprocating compressor. And for us, for our company, I can state in the range of 80% of our compressors, these compressors are used for hydrogen. And what we see, and that is good for us, there are new applications. And we see for the big compressors, if there is an energy in transition, and hydrogen will, or we hope that it plays a major role in the future. And in Europe, there are tendencies to create a real hydrogen infrastructure, means pipelines just for hydrogen. Then pipeline compressors will be needed. And in addition, storage compressors will be needed, because the wind and sun is fluctuating. So there is energy when there's much energy we don't need. And then when we energy need, where there's no wind. So therefore you need the opportunity to store the energy. And this, we hope, will be done by hydrogen, just stored in so-called salt caverns, where here in Europe, in Germany, we have a lot of salt caverns, which are currently used for natural gas, but there are clear projects out to create salt caverns just for hydrogen. And of course, I mentioned it already, if there is in the end an application, for example, the fuel cell, then oil is not allowed to be in the gas, and therefore you need a non-lubricated solution. And as I mentioned, at least up to 200 bar, a non-lubricated solution with a classical reciprocating compressor is not a big deal, it's possible. Yeah, here we had just an idea of the outer dimensions of such a compressor. So this would be a pipeline compressor compressing from 25 bar to 75 bar. We can do it in one stage, pressure ratio of 3. And with this compressor, you could easily reach a mass flow of, let's say, 44,000 kilograms per hour, or 500,000 standard cubic meter per hour. Interesting, very high power, of course, 20.5 megawatt thermodynamic power. Then look at the mechanical efficiency, is very, very low, high. So we have almost mechanical efficiency of 99% for such big frame. So the power shaft is not much above the thermodynamical power. This is a big advantage of it. And then of course, you have to add the electrical efficiency to get the electrical power. Typically, these compressors are run with the electrical motor, not with the gas engine. But of course, in areas where electrical power is not available, then you can also use a gas engine. Important is this number. So the energy ratio, that means the electrical power I need to compress this gas from 25 to 75 bar related to the intrinsic power of the gas itself is only 1.5%. So you don't need too much energy to do the compression work in comparison to the energy included in the gas. Here, this is an interesting map to show you the flexibility of a reciprocating compressor. Here we at the y-axis we have the discharge pressure, in this example from 60 to 90 bar, and here we have the suction pressure from 20 to 40 bar. The black lines are lines of constant flow, and the red and the blue lines are lines of constant power, and the red lines are lines of constant isothermal efficiency. And now you see that this is a main advantage. The efficiency is perfect. So in this case, the design point, we have an efficiency of almost 79% isothermal efficiency, not adiabatic efficiency, and it remains high independently where you are in that area. Wherever you compress, you have a perfect efficiency. And the interesting is you can even improve that just by doing the same compression, no longer with one stage, but with two stages. With the more stages you use, the closer you can come to the isothermal compression. And just for the same example here, the same suction discharge pressure, same frame, we got even more flow, interesting. And of course, more power is clear. But when you look at the efficiency now, at the example before, we had 79%. Here we got even 83% of isothermal efficiency. And when you look in the same performance map, the complete area has almost always the same high efficiency, 81 to 82, something like that. No point is below 80%. So the perfect efficiency wherever you are in this pressure ranges. You can compress whatever you want. The compressor is reacting by itself to the pressure ratio and remains high efficiency value. This is a very interesting point of a reciprocating compressor. And now here, this is a real example. Therefore, I added this picture. In Europe has first projects out for salt cavern storage of hydrogen. Here, typically, we talk about a suction pressure of 40 bar, and the discharge pressure for the salt caverns is typically in the range of 200 bar. So it's clear, the higher the pressure, the higher the density, the higher the energy you can store. So high pressure is needed, and 200 bar is not too low. And for this application with this flow, and this is a real project. So this drawing is made for a project here in Europe. We offered these two compressors, 8-throw compressors, two-stage. And just to give you an idea of the outer dimension of the complete installation. So we have an installation for these two compressors of 60 meters by 40 meters, together with the coolers, which are placed outside. So just to get an idea how much place you need for such compression in the range of course, we talk here about 24 megawatt power per compressor. So this is a 50 megawatt installed power compression. And here you get again the efficiency map. Of course, the higher the pressure, the efficiency goes slightly down. But again, the efficiency is in the range of 78% to, let's say, 83%. So it's again in the range of 80% perfect efficiency. Yeah, let's summarize my presentation. So I gave you an overview of the compression principle. So mainly I compared the positive displacement reciprocating compressor with the turbo compression principle. Physical basis, advantages and disadvantages were presented for the centrifugal and for the reciprocating compressor. And I showed you with the diagrams the efficiency and flexibility advantage of reciprocating compressor compared to all the other compression principles. This is not only valid in comparison to turbo compressors. This is, of course, also valid for screw compressor or whatever you need. So in red, wherever hydrogen is compressed, it is usually a reciprocating compressor, and we as Norma ESSA can really state 80% of our compressors compresses hydrogen, and it would be clear without hydrogen, we have to look for another business model. That's it.
Thank you. Thank you, Dr. Hoff. I appreciate your time. We're running just a little bit behind, so I'm going to go directly to Dr. Jeff Goldmere, who is known as GE's fuel guy. He is an emerging technologies director at GE Power. In this role, he's responsible for developing and executing strategies for the decarbonization of gas turbine-based power plants. Thank you, Dr. Goldmere. Appreciate you being here with us today. I think you're muted.
Here, I just asked the previous presenter, Dr. Hoff, if he would kindly stop sharing so that Zoom will let me just.
What shall I do? Do I share my screen?
No, you just need to stop sharing. It will not let me start sharing.
Excuse me. Yeah, now I see it. Yes, I think now it will work.
Excellent.
Hopefully.
Thank you. All right. Well, good morning, good afternoon to everyone. I know we only have about 10 minutes left, so I will try and go through my material quickly. I've been paying a lot of attention to the questions that have been put up online, so I'm hoping to try and answer some of those as we go along, since we're not going to have a lot of time for Q&A at the end. Look, just a quick overview. We're going to focus really on hydrogen, but I want folks to understand that as we talk about decarbonization, there are multiple paths. We can think of this in really two buckets: pre and post combustion technologies. Pre-combustion fundamentally means, right, we're talking about a fuel that has either no carbon or a zero or net carbon kind of scenario. And then obviously there's post-combustion technologies to remove your CO2 emissions before they reach the atmosphere. So let's focus here specifically on hydrogen. You know, normally I would put in a chart that's got a lot of fundamental physical and chemical properties, but knowing Dr. O'Connor and the excellent job that she was going to do, I decided to take a different approach here. And so just to highlight a couple of the properties that Dr. O'Connor had mentioned and really their implication for gas turbines. So she had mentioned how hydrogen is incredibly energy dense on a mass basis, which is true. But on a volumetric basis, it only has a third of the energy density, which means to have the same energy content going to your gas turbine, you have to have 3 times as much flow as represented by these spheres here, which means the fuel accessory system for a gas turbine has to be sized accordingly. Dr. O'Connor did a wonderful job talking about flame speed. And the reality here in a combustion system, what that means is that flame wants to propagate upstream into the fuel nozzles. And that's typically described as a flashback or a flame holding phenomenon. And again, you know, the velocities of hydrogen, the flame speeds, are an order of magnitude faster. And so you really have to have a combustion system that's configured for that kind of challenge. The other thing to realize is flame speed is a surrogate for reactivity. So it's not just that hydrogen is going to move faster, but the reactions happen so much quicker. So again, your combustion system has to be configured for that. And then as Dr. O'Connor again mentioned, right, the adiabatic flame temperature is hotter. And there was a question asked about NOx. And yes, you will see upward pressure on NOx emissions when you put more and more hydrogen in a gas turbine, because you will start to get incremental increases in NOx. I'm not going to spend a lot of time on this slide, but the concept of using hydrogen as a power generation fuel is not new. In the industrial space, the industry has been using fuels with hydrogen for decades. GE's been doing it for more than 30 years. And you typically see examples of steel mills, refineries, integrated gasification combined cycle plants. You know, overall, this portfolio really represents more than 75 gas turbines and more than 6 million operating hours. I'll point out one specific project here. I guess there have been some questions like, what's the max amount of hydrogen you could do in a gas turbine today? If I look at the top row here, the third picture from the right, it says 1 by GE10. GE did a demonstration project on a unit about a decade ago where we burned 100% hydrogen in a gas turbine. And so you can burn, you know, very high amounts of hydrogen in a gas turbine even today. What I want to point out here is just a couple of specific examples around the kind of activities that you can do. And you can think of this kind of in 3 buckets. The first bucket being, what if you have an existing gas turbine and want to start putting hydrogen into it, but you didn't think about that from the beginning? And so here's an example in that first picture on the left-hand side. We had a customer here in the US who had 7F gas turbines, right? These are notionally 180 to 200 megawatt units. And they had hydrogen available to them because they were kind of a petrochem site. So we retrofitted the system. We provided the picture I'm showing there are 4 fuel blending systems, 1 per gas turbine, that allowed them to blend hydrogen into the natural gas supply at site and allowed them to blend roughly 5% by volume hydrogen to those gas turbines, which they ran for many years. And so you don't have to have a gas turbine configured for running hydrogen at day 1. That's a capability you can add to a system. I talked about the demonstration project we did at 100% hydrogen, but it was a demonstration, not a plant that was in commercial operation for a very long time. But we do get asked, right, is this something you can do commercially? And the answer is yes. So the middle picture here shows a 6B gas turbine. Again, this is roughly a 44 megawatt turbine. It's been operating basically on a fuel that effectively could have either been thought of as a waste fuel that you might flare or a fuel that you maybe would try and make power with. This is a fuel whose hydrogen composition has ranged between about 70% and 95%. And this gas turbine has been running on that fuel for more than 20 years. When we checked on the plant this summer of 2020, the fuel had about 85% hydrogen by volume. So you can configure a gas turbine plant to run on very high levels of hydrogen. Now, these first two examples are ones really where the hydrogen was coming from, let's say, an industrial source. The pivot in the world of the energy transition we live in today is, what if you are now actually thinking about taking hydrogen that was specifically produced because you want to do power generation? And the picture on the right I'm showing is a picture of the Long Ridge Energy Terminal project. This is in Eastern Ohio. This is a project, this power plant will go online commercial operation this year. The plant's owners announced last year that they intend to start running this power plant on a blend of hydrogen and natural gas this year at commercial operation, and transition that power plant to 100% hydrogen in 10 years. So again, questions being asked online, like, what's the maximum level of hydrogen you can do in a gas turbine? You can take a gas turbine to 100% hydrogen. Absolutely. Normally I would spend more time on this slide in terms of talking about some of the specific pieces here, because you have to think about the use of hydrogen in a power plant, not just for the gas turbine. You have to think about the entire power plant. How is the hydrogen coming to you at site, et cetera? You have to think about, as I said earlier, the accessories. How are you piping that hydrogen to the gas turbine? We have to think about things like hydrogen embrittlement, hydrogen diffusivity. Is it going to leak through seals? So you have to have the right seals. You have to have the right steel alloys, right, the right material so that to limit embrittlement issues. Hydrogen, typical gas sensors in power plants are not configured for hydrogen, so you have to make sure that your safety systems are appropriately configured. We talked a little bit about the gas turbine. Again, a comment being asked was around Nox emissions. And so, yeah, you will see from the gas turbine, depending on how much hydrogen you're burning, incremental Nox. But there are ways to deal with it at the power plant level because there are existing technologies. Many power plants around the world are going to run with a Nox emissions after treatment system. They're going to use a catalytic-based system. The industry term is an SCR, selective catalytic reduction system. And that's an industry standard. So there's no reason that if you start using more and more hydrogen and you have increased Nox, to not use one of those systems. The challenges could become, if you have an existing gas turbine, there may be some limits on that system, but there are other things we can do in the gas turbine. So Nox emissions in and of themselves should not be a reason not to use hydrogen as a low carbon fuel. Just going to speed through here. I'm going to 2 seconds on this page. There's really lots of incredible technology development that's been happening in this space. And the one thing I'll mention is GE has some technology we've developed over 15 years with support from the US Department of Energy. It's this combustion system on the far right. It's a new way of injecting fuel and air. If you're interested, I have an article that was published earlier this year in Turbo Machinery International that goes through this. There's a lot of great literature out there that has been published by ASME and others. Lots of great work done by academia as well as the various OEMs in looking at new combustion technologies. What I really want to focus here on my last minute or so are two things. In order to really leverage hydrogen, we have to solve this trilemma. You have to produce it at scale. You have to produce it at scale at a cost that's competitive with other alternatives. And you have to think about infrastructure and transportation and storage. And I really do appreciate Dr. Hoff's comments, his lesson on compression, because you have to be able to move and compress hydrogen. One of the tricks, however, is the existing pipeline infrastructure for gas cannot handle 100% hydrogen. There are significant limits on that. So we have to think about what is the overall infrastructure, and how do you solve this problem of making it at scale and moving it, regardless of whether you use it for power or transportation or such. I'll leave you with one final note here, and then maybe I'll turn it over to you, Jack. I went through this very rapidly. If you're interested in learning more what GE is doing, we've got a real focus on what we call the future of energy in a decade of action. There was a white paper specifically focused on that. There's a QR code that makes that available. As Dr. O'Connor said, we were thrilled to have her as a guest on one of our podcast episodes. Our podcast is called Cutting Carbon, and it focuses on the energy transition and the issues that we face as a society. We're actually in the process of preparing episodes for season 2 that'll focus on hydrogen and carbon capture. So it's a really exciting time. It's a real societal challenge. In fact, it's the challenge of our generation to really help, take this on as a priority. I apologize for having to go through here quickly. For folks who have questions or whatever, hopefully Jack will be able to circulate some. If not, I am available on LinkedIn. Feel free to reach out. Jack, it's 11 o'clock. I'm going to turn it back over to you.
All right, thank you, Jeff. I appreciate your time, and that was a very impressive display of modifying a presentation. I appreciate that. Yes, there've been a lot of questions. It's been a great conversation. Obviously, there's a lot of opportunity out there from what we talked about, but there's still some challenges that need to be addressed. We talked about just the chemistry of it. We talked about moving and compressing the hydrogen, and then burning it has to be done safely. So there's still some work that has to be done. And I want to thank all our viewers who came in today to watch, and I appreciate that. And I think with that, I will say good day.